And good morning, everyone. Welcome to our stream. Welcome to TechWeek 2020. We've been going through it for a few days now. My name is Adahi from Avengers. You're probably getting used to and a little bit sick of my face. But welcome, everyone. We're so grateful for everyone joining us for our stream today. We're going through another awesome lesson. We've got another of our amazing course writers with us today. Hannah, I'll introduce her in just a moment. But first of all, how's your Tech Week been? It's been amazing for us. We've done a few things. We've had some fun going through a course earlier in the week. Our video for that is also here on YouTube. Yesterday on our Facebook page, we had a chat with the amazing Ray from Game 10 about taking your gaming passion into coding. So it's been lots of fun. Today we're going to have a really fun time going through this really awesome lesson that's been developed. It's not just about coding. You take some of that science, stuff that I'm actually a little bit interested in, and we're looking at how it integrates into coding and programming. So we should have a lot of fun. Before I go too much further, let's bring Hannah on. Hannah, let us welcome Hannah to our stream. I really appreciate you being with us.
No worries. Thank you.
So Hannah's joining us all the way from, is it sunny in New Plymouth today?
It is sunny in New Plymouth today.
From sunny New Plymouth. There we go. And we're really grateful to have Hannah with us. So Hannah is our, what's your title again? Product manager?
Product manager, yep.
Yep, product manager. But she's also one of our lead course writers. So a lot of the courses that you have on Code Avengers, those courses that you love spending so much time in, Hannah's there, and she's a big part of the team, either writing or reviewing those. And the course that we're going to be going through today, data representation 4, Hannah was a big part of that one. So we're really grateful to have some of her time to go through this. Before we get into it, Hannah, introduce this course to us. Introduce where our thinking was going into it and what your thoughts were behind as you were building the conception of the course, everything. Tell us, where did this course start?
All right. So this course it's one of our shorter project courses, and it's called Professor Photon's Color Conundrum. This was developed for Hour of Code last year, and the theme for Hour of Code last year was CS for good. So all the ways that technology can be used to do good. So we'll find out a little bit more about that as we're going through the course and how that relates. But the inspiration from the course actually came from my love for or slight obsession with escape rooms. And we wanted to sort of develop a course that would be quite interactive and quite, I guess, full of sort of problem solving and different sort of, bits of science, bits of other things, just to teach some of these data representation topics like binary numbers, and we'll learn about some stuff about light and color and all of that kind of thing as well. So it was really fun to develop for me because I got to think about how to put together some puzzles in an escape room kind of style, but also within that computer science education sort of theme. So yeah, I'm quite a big fan of it. It's one of my favorite ones that I've worked on.
Awesome. And I love escape rooms. If any of you have done escape rooms, they can be a lot of fun. And I mean, so it's not like we're not going to lock you in a room, so to speak, but we do incorporate a lot of those types of puzzles, but also some learning about science and coding and where the two intersect. So it's going to be a lot of fun. Let's dive into it. So this one over here. Ta-da! So just a reminder, this course is available for free. You do not need to have a subscription. You do not need to have even an account with Code Avengers. You can jump on and follow this course. I'll grab the link and I'll throw it into the chat in just a moment. But if you are watching this with your classroom, you're watching this on your own, jump on that link and you can follow through with us and have a great time. So Hannah, take us away. I'm going to throw that link into the chat and we'll go from there.
All right. So the very first scene is actually a video, I think. We'll jump in there and then I think we'll play that video for you so you can see it.
Alrighty, the first video. That's my turn.
Yep.
Welcome to Professor Photon's Color Conundrum. Professor Photon has stolen color from all of the world's digital devices, and you are our only hope to restore them. You'll need to solve puzzles and find your way to her control room. Pay close attention as we brief you on binary numbers for the mission. We usually write numbers using a system called decimal or base 10, with the digits 0 through 9. When we see the number 372, we know that it means there are 3 hundreds, plus 7 tens, plus 2 ones. Computers store data as numbers, using only the digits 1 and 0 to basically represent whether a switch in a circuit is on or off. This is called a binary or base 2 number system. Instead of the columns being ones, tens, hundreds, and so on, in binary they double. So 1, 2, 4, 8, 16, and so on. To work out a number, we add together any columns with a 1 in them. This number has a 1 in the 8 column and a 1 in the 2 column, so we add 8 plus 2 to get 10. This number has 4 plus 2 plus 1, which is 7. Can you work out this number? That's right, it's the number 5.
So, you think you're the key to getting color back? You think knowing a few binary numbers is going to get you into my control room? You'll be telling your grandchildren about the good old days when videos were in color instead of black and white.
I love the voice acting on that. Who was that voice actor for that one, Hannah?
That was me.
It was really fun. I also love how we get a really good introduction to binary. And you guys, if you didn't sort of follow along the video, or if binary is still quite new to you, binary is the base sort of the base language for or any computer system. Yeah, it's either on or off, and it's 8-bit, yada yada yada, and every number value has a value behind it. So, yep, keep up with binary. It's lots of fun. Hannah.
Hopefully you caught a little bit of something from there because it will be useful. So that's our setup for the story. Basically, we have this crazy Professor Photon. She's stolen color from all of the world's digital devices, and the objective of this escape room is to find out what's happened and restore color to the devices. So we have our characters here, Tyrell and Marlee, and our host here at the escape room. So they've got 1 hour to solve the puzzles, starting by going through this tiny door with a flashlight each. So let's see what happens. Whoa, lasers. That's off to a good start. So this part was actually inspired by an escape room that I've done that actually did have lasers like this that you had to crawl between. It was pretty cool. So we're going to click to explore the room with our flashlight and see what we can find. We've got a box with some switches on it. The lasers are in the way. Some ones and zeros painted on the wall.
It looks a little bit like binary.
It does look a bit like binary. It might come in handy. A strange board with some lights on it. Got a box with some switches on it. And we've got a door, but there doesn't seem to be a handle, so I guess we're trying to find our way through the door somehow. Would you like to read some of the dialogue? Or?
Yeah. All right. I will do. Is it Tyrell?
Yeah. Okay.
Yeah. All right. Everything is blocked by the lasers.
Wait, shine your flashlight at the box on the floor. I think I can crawl through the gap and reach it. Click on the box you can reach without touching the lasers. So that's going to be this one down here. It's just a bit of a gap there, just enough space. So we've got 4 switches and a number display. Click next.
All right. I bet we have to put in a binary number.
What number would it be?
It will be one of those numbers.
So what could help us here? We had probably these binary numbers we talked about before. There's 4 digits and there are 4 switches on the box, so that seems like a good bet. Use the image of the numbers on the wall to try to unlock the box. Click the switches to make the first binary number. So, over here we've got 1001, and all of our switches are set to 0 at the moment, so we want to try to make this first binary number, which is going to be...
First switch on, and the last switch on.
And that gives us an 8 and a 1, which makes the number 9. Remembering what our columns were. Now we're going to make the second one, so we've got 0101. That's so no 8s, got a 4, no 2s, and a 1. So that's a 4 and a 1, which is 5. Third binary number, so no 8, but we've got 4,
2, and a 1. Now remember, to those of you that are watching and you're following along with the course, we're going to go through at a nice leisurely pace, but if you want to beat us to the answer, you go for it. And then spam it in the chat.
Thing is just frozen. Hang on. I have to refresh. Sorry, I don't know what happened there.
You got distracted with me blabbing.
It just did a strange little glitchy thing.
So, ordinarily, binary has not 4 digits in it, has 8 digits. Is that correct? Or is it more now?
It just depends what exactly is being used, so being stored. So we'll learn, it comes up a little bit further on in the course, but for example, old forms of text when it was stored, like ASCII is usually 7 bits and extended ASCII is 8 bits. It's strange. Extended ASCII is 8-bit, but then these days we tend to use Unicode, which is like different type of text encoding, which lets us use all the characters from different languages and stuff. And that can be anywhere between 8 and 32 bits, depending on which type of Unicode it is and which character sets are being represented. And I'm not sure why this is not responding, but I might just kill it and start again. Sorry.
All right.
That's good fun.
It's a little bit unhelpful, and now we are extremely white. Haha. Hannah's going to grab that back for us, and that's fine because these things happen. So, okay, not an amazing computer program over here. I have got a little bit of knowledge. So up to 32-bit for Unicode, and it's incorporating multiple language characters. So when we talk about 8-bit, isn't 8-bit normal for like just in our normal computers, like devices talking to each other, or is it still depending on the device?
8-bit is a pretty standard way of storing stuff because 8 bits is 1 byte. So most of what we store and measure and stuff these days is in bytes. So we have kilobytes, megabytes, gigabytes, all of that kind of stuff. But yeah, I'm not like a huge expert when it comes to kind of like networking between computers or interfacing and protocols and stuff. But I imagine a lot of that is probably still done that way, but again, it depends on the thing, because if we're looking at security and encryption and stuff, then we're looking at like 128 bits for encrypting stuff or 256 bits in order to keep up with how fast computers can try to break into things.
We talked a little bit about that with Sarah on Tuesday, and just how fast they can break it if it's just like a 4 or 5 digit passcode, or if it's significantly longer, it's
I think
days and months.
128-bit encryption with brute force guessing, I think it's somewhere around 500 million years to crack it.
No way, really?
Yeah, something like that.
Awesome.
Of course,
All right,
it gets less and less each year, but I think we're good to go now. Let's try.
let's get back into it.
Oh, hang on, this is the first one. Let me skip onto the fourth binary number. So 0110, this time we don't have our hints, but that's going to show us a 4 and a 2, which is 6.
Awesome.
All right.
Go for it.
The box is unlocked, and we've got some playing cards and a piece of paper with 3 numbers on it. So guessing these will come in handy sometime soon, so we'll take them.
I love how in escape rooms you open the box like that and it's completely random stuff.
Yeah.
But there's always everything you pull out is always going to be useful. You just have to figure out how it is going to be.
Yeah, it's usually later on that it shows up and you're like, oh, maybe this is that thing from before.
That we left in the last room.
Yeah.
Alrighty.
All right. We're down to 51 minutes and 13 seconds on our timer, and the lasers have moved.
Ooh, so we can get to some other stuff now.
Yeah, so these ones are still blocked, but we've got another box here that we can get to if we squeeze carefully past those lasers. And this box also has 4 switches. Now we need to work out which item might be helpful to unlock the box. Now, it's possible that it's the playing cards, but we do have some numbers there.
We could make those numbers with the binary switches. Maybe that's a way of helping.
I think we're most likely going to need to do that with one of them. My guess is going to be the number card, because it's a series of numbers like we just did a series of 1s and 0s.
Good guess.
I'm playing along.
Awesome.
It's good. Sometimes you do forget the answers to your own courses when it's been a long time since you've looked at them there. But you have to actually work them out instead of just remembering them. Use a number card to unlock the box. So this time we're working in the other direction. Before we had the 1s and 0s and we just made the switches match, and that gave us our number in decimal. This time we've got the number in decimal and we need to make those numbers in binary. So when you've got a binary number that you need to, a decimal number that you need to convert to binary, the easiest way to work it out rather than just switching randomly is to, if you're quick, you can do it in your head, but otherwise you can start with the biggest switch and you just switch them from left to right. Excuse me. And anytime you go over your target number, you just turn that switch back off. So here we're doing 15, so we'll start with an 8. Yep, that's still less than 15. Add 4, we get 12. Add 2, we get 14. And add 1 and we get 15. And if you remember that the next column is 16, that will make sense why that's all 1s. This time we want a 4, so this one's easy. We just need to click the 4 switch.
Which is the second one along, or third from the right, yeah.
Yeah, third from the right, second from the left. So 1, 2, 4 is our 4. And now we need 11, so we'll start with our 8. And if we add our 4, you can see we've gone over 11, so we switch that one back off. Add our 2, and then we need 1 more to make 11.
Awesome. Now, here's a question that I've got, Hannah, because, I mean, binary, it's everywhere. It's computers and devices are talking to each other in binary all the time because it's their base code. But where do we as humans fit into that? Because we don't speak binary to our computers. We type in with a keyboard or a mouse or touchpad. So where am I going with this? It's for our students that are learning binary, is it still relevant for us to know the basic principles of binary? Maybe not necessarily knowing every single digit, but is it still relevant for us to understand how binary works?
Yeah, I think so. I think understanding how, basically computers are just a big collection of switches, and these switches are either on or off, and as time goes on and computers get more complex, it's just that people made these switches even smaller, and you can fit so many more of them into a computer, and that allows them to do so much more stuff. So it's not that often if you're working in computer science that you would directly work with binary in a computer, but understanding how it works is kind of fundamental to understanding how computers work. And then everything that you learn on top of that is just like another layer of abstraction, or like, a sort of more simplified version that gets to like a human understandable programming language or something like that. But there are plenty of people that work with assembling components that work with assembly languages, which are like even like only a step above kind of the binary layer. So the way of thinking is very much still in that sort of on, off, and just basic logic. I'm working on a course at the moment actually that teaches sort of logic gates and how that works with circuits, and that is kind of like one step up from binary 2, where you're still looking at whether some inputs are on or off and whether the output is on or off, but you're adding in logic so that there's reasons why, different combinations of things that will turn circuits on or off. And I think once you understand binary, then if you learn a bit of logic gate stuff, then that really gives you a good insight into how these circuits are working and making decisions and doing all of the computation that leads to stuff like, making YouTube videos or playing games or all of that kind of stuff.
Yeah, I also think just from what I was thinking when you're going through that was, if you're going into electronics, then understand like the interface between software and hardware. You're going to need to understand binary, even if you are using another layer above binary. You still need to understand it so you can understand how to get software to talk to a given piece of hardware.
Yeah. Yep, absolutely. And there's other numbering systems that get used in computing as well, like hexadecimal, which gets used for the sort of color codes for websites and things like that. So, once you've learned base 10 numbering, which is our usual decimal system, and then you learn a bit of binary, then understanding how number systems work means that, there's other things you can learn in other applications and different parts of computing as well.
Sorry to distract you.
No, all good. All right, so inside this box, we've found a strangely written note that says, "Nobody I don't know enters my control room without the secret number. You don't deserve color in your devices." Guessing that's from Professor Photon. And we've got a card with a letter and some numbers on it. So we will take them and see if we can work out what to do with them later.
Oh, sorry. Now we can reach that light board.
All right, so this is our light board. If we click on the lights, they turn on and off, and we have to turn them on in a particular pattern, and this is our clue. So we've got a 9 and a 10 of clubs. Excuse me. And yeah, we have to, can we see anything on this side that looks like we could use it over here?
The only thing that I can see, like the 9 and the 10 are really stumping me. I'm not sure what's going on there. But on the flipped over card where you can see the back, there's actually a difference where the colors are inverted for some of the squares. So that might be a clue there if we put that into the light board.
That is true. These ones white in the middle, red on the outside, and those ones are the opposite. So if we click like that.
It looks like a 9, but I don't think it's supposed to look like a 9. Oh, it's a P. Yeah, it's a P.
PP. Guessing that's another subtle message from Professor Photon.
Oh, I got it. The lights are on and the lasers are gone. We are amazing.
Now, how do we get through that door? Got a light beam and a panel here that we can investigate, so we'll give that a push. And it's revealed some more switches. Now we need to work out what might help us unlock this door. So we've got our flashlights, but I don't think that's going to help us much now that the lights are on. Our number card, but we've already used that one. So it looks like it's time for this strange note.
That's a funny, strange note.
So we need to solve the riddle and then type into the box the number that's needed to open the door. So somewhere out of this riddle we've got a number. Nobody I don't know enters my control room without the secret number. You don't deserve color in your devices.
Now, for me, I noticed that there are some random capitals spread throughout this note. Maybe the capitals form a word?
Yep, that seems like that's probably the one notable thing about it. So let's have a look at the capitals. We've got N-I-N-E, it's 9-T-Y, 9T, and then S-E-V-E-N. So it says type it as a number, so that looks like 97. Nice.
97. I was just writing down a piece of paper. You're too fast for me.
Sorry.
You're fine. All right. So now I'm guessing we have to make 97 using this 8-bit binary code, a binary switch.
Yep. So with the smaller numbers, the method I was showing about starting from the left and using the biggest ones first isn't as helpful with 4 bits because you can remember that they're 8, 4, 2, and 1. But with a bigger number, it can be a little more helpful. So we'll do this. This is our 128. That's
Ooh, way
too big. 64, we'll keep that because that's not over. We're adding a 32, it gives us 96. And because we want 97, we can skip those and just add a 1.
We know it's just going to add one more to make our 97. Cool.
Yep.
We are becoming
All right.
pros at binary.
We are. The door is open, so I'm guessing that's probably not the exit there, because escape rooms usually have more than one area. Oh, there's more.
There's always more.
There's always more. Down to 42 minutes and 16 seconds. Making good time though, I think. This room has a timer on the wall and a small table in the middle. Click the left wall to take a closer look. So let's explore over here. See what we can find.
A door.
We've got another mysteriously locked door that we're not sure how to open.
People should put handle on the outside of doors. Just saying.
Yeah, it would make it easier. We've got a plant that looks healthy. That's good. Someone's taking care of it. And we've got a cupboard which is locked and there's a grid on it. So I guess we should remember about that grid. And now we're going to have a look at the right wall.
Speaking of plants, it sounds like a lovely productive lawnmower on your end, is it?
Yes.
Good on
Sorry
them.
about that.
No, it's good. It's good to be productive with your time and mow the lawn.
It's probably the neighbors.
Good on them.
Well.
That's fine.
All right. Explore the bookshelf. These books are stuck to the shelf. This book is about light theory. We've got another book called Picture Elements. And those ones are nothing. You know, I don't know if you've done many escape rooms with bookshelves, but they always have like the books that are glued to the shelf.
Yeah.
That are just like the decoys.
There's always that one tiny book that you can finally get out.
Yeah. And this book is about RGB. So we shall find out some more about that. Take a look at this light theory book.
I always loved these topics when I was going through high school. Light theory and sound that were always interested me. So sorry, we'll carry on.
No, it's good. I enjoyed that too. All right. I'll start and read some of this. So light is a form of electromagnetic radiation. Light is made up of photons, which are like little packages of energy. White light contains.
White light contains lots of waves, which all have different wavelengths and frequencies. The different wavelengths appear to us as different colors. Infrared waves have a frequency that is too low for us to see, while ultraviolet waves are too high. We call the wavelengths in between the visible light spectrum.
Sweet. So basically anything that's below red or above purple we can't see, but we can see those colors in between. And speaking of colors, when we see objects, we generally see them in color. Molecules in the object absorb some wavelengths of light, but others bounce off. The ones that bounce off are seen by our eyes, and the combination of those is what gives the object its color. And because white light is a mixture of all of the different colors, we can use a prism to split white light into a rainbow. So if you've ever done that experiment in physics class, or if you've got some of those little kind of prismy things that you hang in your window and you get the rainbows all around the room, that's why.
Yeah, that was super cool. I used to love doing that. It was super trippy. You always got to think, who was the first person that figured out you could do that? And why? How did they figure that out?
Yeah, that's a good question. I feel like that's something I probably learned in science at school, but don't remember now.
Well, for me, it's more like, it's
Yeah.
kind of like an egg. Like, who thought that eating that egg was a good idea?
Yeah, I've definitely had that thought before. Someone, I suppose back in time when people didn't have computers and stuff, they had to entertain themselves somehow and just experiment with stuff.
Yep.
Prisms and eggs and all sorts. All right, a couple of questions based on what we just read there. True or false? White light is made up of every color we can see.
This is true. Every color we can see and a few others we can't see.
Yep, that is true. All right, now we're going to learn about picture elements, which you probably know more about than you'd think if you might just not recognize the name. Picture elements are better known as pixels.
Oh, awesome.
So computers, including phones and tablets, display images on the screen. The screen is made up of lots of little squares called picture elements, or more commonly, pixels.
On the very first screens, pictures were displayed using only two colors. The pixels were either on or off. For the computer to store these images, it only needed one bit, one binary digit, per pixel. This allowed the screen to display simple images like this. I remember playing that game. Just
Me
saying.
too. Good old Pong. You can see here these little squares would have been a pixel each, and some of them are on, some of them are off. But over time, screens have become more complex, being able to display colors and having more and more pixels to display images with more detail. Would you like to?
Yeah, sure. Computer storage has also gotten bigger and cheaper, making it possible to use more bits per pixel so that more than two colors can be used. For example, 2 bits per pixel allows 4 colors, 3 bits per pixel allows 8 colors, and then we're going to skip a bit, 8 bits per pixel allows 256 colors. So we're really getting out there.
So this picture here would probably be one of these 256 color ones, or probably almost 8 colors. There's not that many colors in that picture, are there? But so just for example, with 2 bits per pixel, you get your 4 colors, because with 2 bits you can have 0, 0 as your binary numbers, 0, 1, 1, 0, and 1, 1. So that lets you use those 4 numbers to represent a color each. How many bits were used to store the data for pixels when screens were black and white?
Just one.
Just one. Yep, so we could have, with 1 pixel, we can have on or off, and that gives us black and white. Have a look at this RGB book. True color. Modern screens use what's called true color. Each pixel contains a red, green, and blue light. Each color can be varied in brightness on 256 levels, from 0 to 255. So that gives you 256 different numbers, including 0.
This allows for over 16 million colors and means there are enough different colors available that the photo looks to the human eye just like the real thing would. We can't see any more than those 16 million colors, so that's why it's called true color.
So that's pretty interesting. So we don't actually need to use any more bits to represent colors than that, because we can't see any more colors.
Sorry, just one. So we've got three three lights, three lights, red, green, and blue, and each of those is an 8-bit. Each of them has 8-bit code behind, binary code behind it. And then when you combine any combination of 0 to 255 brightness with each of them, that's what generates our colors. That's amazing.
Yep. And so if you've got 256 levels for each color, then 256 times 256 times 256 gives you the 16 million something something something. Yeah. So basically over here, that's what we're saying. So that to get those 256 levels of color, we've got 8 bits for each color. So 8 bits for red, 8 bits for green, 8 bits for blue. So that makes it 24-bit color overall.
Computers store the values for these colors as 24-bit binary numbers. 255 means the color is all the way on, and 0 means it's all the way off. So red is 255, 0, 0, as shown in the colors. RGB colors can have any values up to 255, like that's a very different color blue, like Dodger blue, and it shows its code down there. So 30 red as displayed in binary, 144 green, and 255 blue, which is all the way on blue. So that's really cool.
Yeah, it's quite cool when you look at the numbers, because you can see that Dodger blue is mostly blue, and then like
A little bit of the other ones.
half green, and then just a little dash of red.
Yep.
Which is handy. Which 3 colors are used in pixels on true color modern screens?
Red, blue, and green.
It's our RGB colors.
Which is funny because in printing, they use a different set of 3 colors to make the combinations for printing, which we're not going to talk about right now.
Yeah, difference between adding light together versus adding ink together. All right, so we just read those 3 books, and after we'd taken the 3rd book off of the shelf, this red book is now sticking out. We need to pull out 2 more books to solve the puzzle. Any guesses which books they might be?
R, G, B, green one, and the blue one.
Green one and the blue one.
A secret compartment has emerged.
Got a little hatch that's opened.
Cool.
And there's a prism. Take that. Sounds like it would be useful. Now, what did that book say about prisms again? We could put it somewhere. It might give us some kind of result.
Where there's white light, so we can split the light.
Let's split this. Oh, cool. We got a rainbow and some binary numbers on the wall over there. Now, these are going to be useful for something, and can we remember something that might kind of resemble that?
There was a little codey bit on the left box.
We had a grid on this box
Yep.
over here, didn't we? Let's take a closer look at that grid. So we've got a whole bunch of pixels, and we've got zeros and ones, and we're going to turn on the ones with a 1 and leave off the ones with the 0 so that we can...
So we're doing exactly what a screen would do with, if this code was to come through, doing exactly the same thing, just manually, bit by bit.
Yeah, pretty much. We're just...
And a lot slower than the screen does.
Yeah. Can't click that fast, but... Alright, inside this cupboard we have got a key. We'll take that. Got the number 166. We'll take that. And we've got another one of these cards with the letter and numbers. Those numbers are starting to look a bit like the RGB colors we were just looking at. So keep that in mind. Something's changed, and it's our door. It's got a way to open again. 34 minutes. Choose the item you haven't used that might help unlock the door.
Mm-hmm.
What do we reckon?
The number 166. We have used the other one so far.
We have.
It's obviously not a key.
It doesn't look like a key. A keyhole door.
Unless you're going to like smack it against the switches.
Yeah. So we need to make 166. So we'll use our strategy, our algorithm from before. 128. We're not over. That's too big. That's not too big. Add 16. We've gone too far. 8 too far. 4 and 2. There we go.
Awesome.
So it's our binary number for 166. Door is open. Click next.
Hooray! Phew!
We better hurry. There's still another room.
Another room.
There
Crikey
is.
Jack.
All right, click to explore the room. 25 minutes. So we've got a TV, got a door that once again doesn't have a handle and it's locked. Speakers, binary switches, papers. Someone's left a coffee there. Got a locked drawer with a weird circle on it, drawer with a keyhole, and another locked drawer.
Alrighty.
Click on the drawer you can unlock.
We have a key. We can do the
have
key
the
one.
key. Let's give this one a go. Choose the key to unlock this drawer. And we've got another card.
We've got 3 of those so far.
Yeah, we do. So I guess they're going to come in handy. Something's changed. Oh, got color on this thing over here. Open that up.
It's a color puzzle.
Some of you guys might remember these from the 80s and 90s. We've got to get through 7 rounds. I'm not sure if you'll actually hear the audio from here, but you'll be able to see the lights and the flashes anyway. So do my best to copy this and get it right.
The blue.
Hmm.
3 blues. Blue, 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 yellow, green. Yellow, green, red. Blue, yellow, green, red, red.
Cool. Now we can pass, so I won't keep you here forever watching me play Simon.
But if you really want to,
you can play it for as long as you can. Whoa, we found a tablet, another one of these cards, and a pretty picture. So let's take them and see what happens next. Oh, we found a tablet.
turn it on. Let's see what it does, because that's what we do with tablets. You just find a tablet and just turn it on, you know?
Yeah. All right, we've got 2 apps. Let's see what this first one is. All right, it's an RGB color mixer, so we can
Ooh, that's really cool.
slide these to make colors, and this part in the middle is the color that we're making. So that kind of orange, yellow, heading towards white, purple, pink, kind of thing. You can see the RGB numbers down here too. So if you can make Dodger blue if we go like, I think it was like 31,
144 and for what?
5.
It's pretty close to Dodger blue.
Pretty close. I just didn't do that accurately, but yeah. Ooh, that's how that works. And then this app with the eye.
Where does Dodger blue come from? Is that like your favorite color?
It's one of my favorite just web colors that has a name. It's a nice shade of blue. Color blindness. Okay, this is going to tell us a bit about color blindness. That's interesting.
Cool.
Color blindness is one of the most common sight issues. It occurs most often in males and affects 4.5% of the population.
Cool. Types of color blindness. Okay, maybe you should do this part because I don't know if I can pronounce this.
All right. Types of color blindness. We've got protonomaly, which is red weakness. So when people are colorblind, they can either have weak sight for that color or no sight for that color. So protonomaly is red weakness. Protanopia is red blind. Deuteranomaly is green weakness, one of the most common types. Deuteranopia is green blind. Tridanomaly, blue weakness, and tridanopia, blue blind. People with protanopia and deuteranomaly find it difficult to tell the difference between red and green, and people with tridanomaly find it difficult to tell the difference between yellow and blue. There's a link here if you're on the course. You can go read a bit more about color blindness as well.
That's cool. I didn't know there was different types of color blindness. I thought it was just mainly red.
Yeah, it's red and green is really common, but the other types do exist. All right, so let's see what this app does now. We tap red, turn it on, off. So this is showing us basically what it looks like for people that have red color blindness, green, blue, and also we've got some labels that just show what the colors are. So yeah,
Because
like
everything looks very blue on that one, but
yeah.
Ah, cool.
Tyrell, this is a color blindness app. My dad uses one. We can see what things look like to him, and he can use it to see what color things actually are.
Oh, do you think Professor Photon is colorblind?
Maybe. So here we are looking at some of the CS for good type stuff.
Oh, Marlee, I think those cards we've been finding are RGB colors in binary.
We must need to convert them to decimal, then use the color mixer app to work out what colors they are. Alright, we're onto something. Click on the item in the room that can help convert the RGB binary numbers to decimal. Well, we've had lots of practice using switches, so seems like a good strategy. Right, Marlee and Tyrell have done the first couple for us, so we're going to do the next few. Do the red color, so this one we're just putting the binary numbers in.
Yep.
And that gives us 30 for red. 1001000
Oh, it's gonna be Dodger Blue. I don't know, I'm just guessing.
Yeah, it actually is by the looks. 3144 and 255.
Just keeps coming back.
11110010.
So this one's gonna be quite a red color, isn't it?
Yeah, it's quite a high red. And then oops, 111.
Quite high green too.
00011.
What's a high red? It's to be a yellowy color if the blue is low.
Yep. And 1010. 10. Yeah, so that could be yellowy color.
Yellowy orange or something like that.
So now we're going to work these out and match up the colors with them, so we can type the numbers in here, or we can drag the sliders to roughly the right spot. So 1272550, I'm going to call that green.
Funny how green has such a high component of red.
Yeah.
That
looks like purple.
Purple.
And we know that one was blue and that one was yellow. They just happened to be in the right spot, and we'd already worked them out anyway.
Awesome.
All right, we must be getting close. Oh, we're up to the riddle video.
Let's have another one.
You think you're clever, huh? Well, let's see what you make of this riddle. 4 friends are going to the movies. They are waiting in line. Sam is ahead of Max, but Max isn't last. Alex is after Sam, and Chris is directly before Max. What order are they standing in?
Alrighty.
Alright, so we've got a riddle about Sam, Max, Alex, and Chris. Which one of these looks useful?
Once again, it's going to be not the key because it's not really helpful.
Yeah.
So the RGB color cards.
And we've got some letters here that go with those names, so that seems like a good bet. Alright, now we need to solve this riddle and sort them into order. 4 friends are going to the movies. They're waiting in line. Sam is ahead of Max, but Max isn't last. Alex is after Sam, and Chris is directly before Max. So, we know that Max isn't last, and we know that Sam is ahead of Max, and we also know that Chris is before Max. So Max needs to have 2 people in front of him or her.
And Chris is right before Max.
Chris is directly before Max. And
Alex
Sam is
after
ahead of
Sam.
Sam is ahead of Max, and Alex is after Sam. So Alex is actually last, which is still after Sam. That's we're gonna have to do that. Sam,
That's right,
Chris, Max, Alex. That's the one. Now what's changed? Oh, we've got 8 minutes left. 4 buttons have appeared on the door. We have 4 color cards and there are 4 buttons.
But the colors don't match.
I think we need to push them in order. We just have to figure out which color is which. Now, what could we use to work out what the colors actually are?
I think Yeah, the color blindness app, because those look like they might be not what a normal person would see, but what a person with a color blindness condition might
So
see.
yeah, so if we can get this to tell us what those colors actually are, that should help us. Alright, tap the round buttons to find out what each color is. That is yellow, that is purple, that is green, and that is blue. So when we put those cards in order before, they had the colors written on them. So we've worked out the order that we need to push them in, which is blue, purple, green, and yellow.
Awesome.
So we will go blue, purple, green, yellow.
They don't look like the colors they stated as, but then that's what a person with a color blindness condition would see it. So it's really good for us to understand that.
It is, and I actually did those colors specifically with like a color blindness filter to make them the right shades for the colors that they actually were. So
that's cool. All right, we did it.
But we're almost out of time. Only 5 minutes left. Quick! Ooh, now we've got this panel on the door. That looks fancy.
This is a really fun activity, guys. You can spend a lot of time here.
Solve the puzzle. Alright, so what we've got is a grid, and we've got a bunch of numbers and colors over here. And if we look carefully, we can see this one says 10,000, which is our white. And that is 10 squares of white. So that seems like a good pattern to follow. Then we've got 3 white, 4 red, 3 white. So let's carry on like that and try and match it up. So here we are, 1 white, 1 red, 1 orange, 4 yellows,
orange,
1 orange, 1 red. Oops.
Oh,
I just painted over it. 1 red. And then we just do it. That's got a red and a red there. It's got an orange and an orange there.
So it's actually really funny. This is a really simplified version of what our computer screens or our phones are doing every single second, but in so much more complexity and way faster. So it gives you an appreciation of what our computer screens have to do to keep up with us.
Yeah. I'm trying to be as accurate as I can here. Should have put my mouse on a higher resolution. And 4 indigos in the middle there.
We just need another yellow on that line as well.
Oh, whoops.
Yep, last one.
I missed that. Yellow. We've got green, blue, indigo, 4 violet, here, blue, green, blue, on that side, indigo, violet, 4 whites,
some whites,
violet, indigo.
So it's interesting as well. So you'll notice if you're watching this, Hannah kind of knows because the pattern is symmetrical, like what it's going to be. But a computer that doesn't know has to read those instructions, has to execute every single line at the same time.
Yeah, I'm using a bit of just deduction to put that together. But yeah, a computer would do that exactly square by square.
Humans seduce, computers just follow the instructions exactly, and they do it so fast.
Yeah. All right, 2 minutes 23. Click on the door to exit. I think might have made it. Congratulations, you successfully escaped Professor Photon's color conundrum. Did you find out anything interesting about her? That's Marlee. We think Professor Photon is colorblind. And here we are with the last video.
Alrighty.
Yes, I took away the color because everyone takes it for granted. You needed to learn about light, color, and how screens work so you would appreciate it more. And you had to navigate the last room using the kind of technology I use to help me every day. Perhaps I overreacted. But the more people are aware of what the world is like for people with disabilities and how computer science and technology can help them, the more people will factor that into their designs, making things that little bit easier for people like me. I never expected you to crack my run length encoding puzzle on the final door, though. Maybe you just got lucky, so I'll explain. Run length encoding is a type of compression. Compression makes data smaller in order to store it.
There's more.
Instead of storing a color value for every single pixel in the image, we store how many pixels in a row there are of each color. When there are runs of similar colored pixels, this reduces the amount of space needed to store the data. When you decompress it, or turn it back into the picture, like you did on the door, you get the same picture you started with. This means it is lossless compression. You don't lose any information. Well, now I must go and redesign my control room. I can't have it so that civilians like you have access to the unimaginable power within it. However, you can draw one more picture on the pixels if you'd like. Goodbye.
It would have been a lot of fun doing her facial expressions, I think. She's just like, ah, so there's eyebrows going at it.
Yeah, that was fun. I was like, she's going to have to be a little bit expressive to get the mad professor vibe across.
It was fun.
Yeah, so basically, I mean, that's how the CS for Good theme tied in. Basically, it was just understanding a bit about how technology can help people with different types of disabilities and things like that, including color blindness. And it's one of the reasons why it's good to have diversity in tech, because people very rarely think of solutions to problems that they don't have personal experience with. So, yeah.
Oh, that's awesome. Cool. Does that bring us to the end? I think there's one more activity that you can do afterwards on your own, eh?
Yeah, so at the end you get this nice little pixel paint grid, so you can, draw yourself some whatever you want. Little flower. Because I'm
cool.
really good at it.
Cool. That's awesome. Alrighty. Well, thank you so much, Hannah. So that you can spend a lot of time on this one, especially if you do the RLE code and send it off to your friend and they have to decode it. And you can sort of pretend that you're a computer screen monitor and you have to decode things. It's a lot of fun. But thank you, Hannah, for your time. It's been a lot of fun doing this course together and going through that. I love what you said about how diversity in programming is essential. So we talked about color blindness, but there are so many other either conditions that people may have, which we should think about and cater towards, or maybe just differences in the way that we think, our backgrounds, and all of those add to the, how do you call it? All of it adds to the value of what we program and what we develop, and how we learn as well. So awesome. What do you call it? Positive computer science.
CS for Good was the theme, but
CS
that's the same thing.
Yep. No, awesome. Alrighty. Well, Hannah, any last words as a chief writer for this course? Anything else you wanted to share with our audience?
I don't think so. Just if you haven't had a go at going through some of these courses and our free activities, they're a great place to get started and just try out and see what kind of things we offer. And then obviously our full courses are longer and have even more activities in them. And yeah, just encourage you to give it a try. And yeah.
Awesome. Thank you so much, Hannah. Thank you so much to all of our viewers for spending some time with us. We really appreciate it. And ka kite, we'll see you another day. Bye.